Hi, I'm Mark, and this is an AP Physics 2 video. I like my coffee black, with no sugar and no milk, but suppose you like milk. The coffee is hot, fresh out of the coffee pot, and the milk is cold. You like your coffee to be nice and warm, as hot as possible. Suppose you're interrupted before you get a chance to pour the milk in the coffee. You know that you want to come back to hot coffee. Should you pour the milk in right now? Or should you wait and pour the milk in after you finish with your interruption and you come back? That's a question for you. So, I'm going to show you a way that you can collect some data which will help you answer this question if you think carefully about the data. This is a Vernier temperature sensor, temperature probe, and a LabQuest 2. It's about 22 degrees Celsius in this room. And this is just an old film can from the days of 35mm film. You can use anything, although it's nice if whatever you use has a lid. A styrofoam cup with a lid works well. So what I would do is heat this to a nice hot temperature. When I collected my data earlier, I had it at about 75 degrees Celsius. That's a good temperature to model the coffee. And then just insert whatever device you're using to measure temperature and record temperature over time data. Then look carefully at your graph and think about what that graph says. It'll have an answer to the question, should you pour the should you pour the milk in first, or should you wait until after the interruption is over and then pour the milk in?
Okay, here's the data that I collected with the little black film can, some 75 degree Celsius hot water, a Vernier temperature probe, and a LabQuest 2. I've taken the data and I've imported it into the computer, and I'm looking at it in Logger Pro, which is Vernier's computer software for data analysis. Notice I collected data for about 10 minutes, 600 seconds, and there are 2 samples collected every second. I'm going to try an automatic curve fit on this data and see what looks like a best fit. I've got a couple ideas. It's a concave up curve, so maybe I'll try a quadratic, because those are pretty common in AP Physics. So there's our quadratic, and it looks like a pretty good fit to some of the data, but look what happens when we zoom out. It looks like it fits the data, but then when we get beyond the data, the temperature continues to decrease for a little while, and then it starts going back up again. That's as if our coffee, while left alone, got hot on its own. That will never happen in the real world, so this can't be a good fit to the data. Of course, I've done this lab before, and I know a little something about this situation, so I know what the best fit will be. I'm going to use a natural exponent fit. This is a very good fit to the data, but unlike the quadratic, it makes sense when we go beyond the bounds of the data. The temperature will continue to decrease and will eventually flatten out and reach what's practically a horizontal line. In this case, it only goes to about 45 degrees Celsius, but remember the temperature of the room? If I'd collected data longer, we would see a function that would eventually flatten out at around 22 degrees Celsius. I was just impatient because I wanted to get this video done. Here's the data from Logger Pro. The purple are the data points. The thin black curve is the best fit. The best fit function is up here. A little bit more about that in a moment. And these 2 tangent lines represent the slopes of the graph at the beginning of data collection and near the end of data collection. This first tangent line is steep. That's where the temperature of the coffee is high and the coffee is cooling quickly. The second tangent line is less steep. That's where the temperature of the coffee is cooler. It's lower temperature, and the coffee is cooling more slowly. This horizontal line represents where the curve is going over a very long time. After a very long time, this curve will flatten out, and the temperature of the coffee, I'm sure you'll agree, must be room temperature. I did not carry out data collection long enough for this to be an accurate room temperature, but with perfect data, that would be what it would represent. Now let's look at the function. The function is for temperature in Celsius, and that is equal to 30 times E to the negative about 0.002 T plus 44. So what do each of these numbers represent? Well, the 44 must be room temperature because this exponent is negative, and as t gets very large, then that number must go to 0. So the function will end up equaling 44 after a very long time. That's our slightly inaccurate room temperature. This number actually represents the temperature difference between the coffee and the room at the beginning of the data collection. And the exponent times t, well, that's a constant that represents the physical properties of the system times the time. You don't actually have to know anything about this function for AP Physics 2, but it is a good example of an exponential function, and it's interesting to think about. Here's an analogy that helps me think about the coffee cooling off. Imagine that this tank of water represents the energy in the coffee. When the temperature difference between the coffee and the surroundings is high, then the energy leaks out quickly. When the temperature difference between the coffee and the surroundings is low, then the energy leaks out slowly. So by shifting the curve, by adding the milk early, you shift the drainage of the energy from out of the coffee into the environment to a slower rate, and that allows the coffee to stay warmer longer. On my screen you see a simulation, the FET gases intro simulation. We can use this to help understand why it's better to add the milk to the coffee right away in order to keep the coffee as hot as possible. What you see is a gas in a box simulation. There are many molecules of gas inside a box with a thermometer showing that they're at about 300 Kelvin. They are moving around the box, bumping into the walls of the box and into each other. In this simulation, they're not allowed to transfer energy outside of the box. But in a cup of coffee, there would be molecules of liquid moving around, not as freely as the gas, obviously, but they would be in contact with each other and moving around rapidly and bumping into the container and into the air surrounding the coffee at the surface. So let's look at what happens when we change the temperature and infer from the motion of these molecules what would be happening with the energy transfer in the cup of coffee. Notice that there's a little sampling device here where I can see an estimate of how many wall collisions there are in a short period of time, 10 picoseconds. Looks like at 300 Kelvin there are about 190 wall collisions in every 10 picoseconds. So now, by heating, we can change the temperature and model the hot coffee. Now I'll collect the number of wall collisions. Notice there are many more wall collisions, around 230 instead of 190 or so. If I cool it back down, the number of wall collisions decreases. When the coffee is hot, it's like the gas that's hot. It has many collisions with its coffee cup, and it can transfer energy outside of the coffee cup with each collision. When you add the milk, you reduce the number of collisions in any instant of time, and you reduce the rate of transfer of energy outside of the coffee. So if you want to keep your coffee as hot as possible, you add the cold milk. Now you might say to yourself, that seems really odd. But remember, the milk is not at absolute zero. It's cold, it's what we say is cold, but it actually has energy. Its molecules are in motion too. So you're actually adding energy when you add the milk. You're not adding something that's called cold because there is no such thing. And when you add that milk, you reduce the rate of energy transfer outside of the coffee. I hope you liked this video. We answered the question of the coffee conundrum. Now you know that you should add your milk immediately if you want your coffee to stay as hot as possible. We saw that in two ways, by looking at the slopes of the graph of the data and by thinking about what's happening with the microscopic model of the materials that we are talking about: the coffee, the cup, the air. One thing I was unable to do because I only had one temperature sensor was to set up two cups of coffee side by side, one with the milk added immediately and the other with the milk added later, and we could compare the curves. And I didn't take the time to do that with the one temperature sensor, but that would be kind of an interesting way to look at this little lab or demo. Thanks for watching. Any questions or comments, please let me know. I hope you liked this video. We answered the question of the coffee conundrum. Now you know that you should add your milk immediately if you want your coffee to stay as hot as possible. We saw that in two ways, by looking at the slopes of the graph of the data and by thinking about what's happening with the microscopic model of the materials that we are talking about: the coffee, the cup, the air.